Today, we're diving into few-shot learning, a really fascinating kind of AI that is tackling one of the biggest and maybe strangest paradoxes in all of modern science. Let's just start with a number: 20 terabytes. That's the absolute flood of data that just one new telescope, the Vera C. Rubin Observatory, is going to create every single night. This mind-boggling scale, well, it creates the massive problem that we're about to unpack. You see, we're in this weird new era. We have these incredible instruments that are generating more data than ever before in human history. But here's the paradox. Finding those truly new scientific discoveries, the needles in this cosmic haystack, it's actually getting harder, not easier. This quote just nails it, doesn't it? We are literally drowning in data, yet starved for knowledge. And this is the exact problem that a new kind of AI, few-shot learning, was built to solve. So the real issue here boils down to something called label-poor data. I mean, think about it. That 20 terabytes from the observatory or the billion particle collisions a second at CERN, almost all of it is just unclassified noise. The discoveries, the things we actually care about, are incredibly rare. It's physically impossible for any team of humans to sift through all that.
And this is where our typical AI playbook just hits a brick wall hard. A standard machine learning model needs hundreds, maybe thousands of labeled examples of a supernova to learn what a supernova looks like. But what if you're looking for something brand new, something no one has ever seen before? Well, you have 0 examples. The whole thing is a non-starter.
So if the old way doesn't work, how do we solve this? Well, the solution comes from mimicking something that you and I do completely effortlessly: learning from just a tiny handful of examples. Okay, let's play a quick game. Imagine I show you 2 pictures of an armadillo. Then I show you 2 pictures of a pangolin. Your brain just instinctively starts comparing them, right? You notice the different ears, the size of the scales. Now, if I showed you a 5th, new picture, you'd probably know which one it is instantly. You just learned to tell them apart with only 4 total examples. That intuitive leap is exactly what we want to teach a machine to do. And that little game we just played, well, that brings us right to the definition. Few-shot learning, or FSL, is just a machine learning framework designed to do exactly what you just did: make really smart predictions based on a tiny number of samples. It's about learning how to learn. Now, there are only 2 key terms you really need to know here, and they're super simple. That small collection of animal pictures you learned from, that's called the support set. And the new mystery image you have to identify, that's the query. That's it. That's the basic setup. Okay, so we know what it is, but how does it actually work? This is the cool part. The secret isn't about memorizing examples of animals. It's about understanding relationships. This right here is the biggest mental shift you have to make to get FSL. It's a huge change in thinking. Traditional AI learns to classify. You feed it 1,000 photos of tigers so it can learn to say that is a tiger. But few-shot learning, it does something different. It learns to compare. It learns to say these 2 things look alike or these 2 things look different. So the whole goal isn't to make the model an expert on tigers or pangolins. The goal is to train it on a massive, diverse data set of all kinds of things, so it develops a universal similarity function. It builds an expert intuition for what makes any 2 things alike or different, even if it's never seen those 2 specific things before. And this is where it all gets really, really exciting. Because this simple but profound shift from classifying to comparing is having a revolutionary impact across pretty much every field of science. Let's take a look. First up, let's go back to astronomy. The main goal of these huge new telescopes isn't just to find more of the stuff we already know exists. It's to find what scientists call the unimagined, the cosmic phenomena we can't even predict yet. So get this, in a recent breakthrough, Google's Gemini model was shown just 15 examples of real versus bogus cosmic events. 15! With only those few shots, it learned to filter that nightly 20 terabytes of data with over 90% accuracy. And here's the real kicker. It could explain its reasoning to the astronomers in plain English. Now, let's see how this exact same idea can be applied in a totally different world: genomics, and specifically the incredibly difficult challenge of diagnosing rare diseases. There are more than 7,000 known rare diseases. Now, a traditional AI would need thousands of patient examples for each one of those. It's mathematically impossible. For a lot of these conditions, there might only be a handful of known patients on the entire planet. This is the ultimate few-shot problem.
Okay, for our last example, let's head over to the Large Hadron Collider at CERN. For decades, physicists have been on the hunt for new particles beyond our current understanding, but it's an incredibly hard search. FSL is helping them hack this process by getting around a huge fundamental bias in how they look.
The old way was to train an AI to look for the specific signature of a particle you've already predicted might exist. You're searching for the needle. The FSL approach flips that on its head. The philosophy is, don't search for the needle, learn the haystack. You train the model on billions of simulations of all the physics we already know, teaching it what normal looks like. Then you just let it loose on the real data, and its only job is to flag anything that looks weird, anything that deviates from normal. It's a completely open-minded search for anomalies we haven't even dreamed of yet. So when you pull all of these pieces together, what you're really seeing is the emergence of a brand new kind of scientific partner. You're seeing the rise of the AI co-scientist. We've seen FSL play three really clear roles. In astronomy, it's the filter, an expert assistant saving scientists from being buried in data. In genomics, it's the bridge, allowing knowledge to transfer from data we can simulate to help diagnose real patients. And in physics, it's the sieve, this unbiased tool for catching the things we didn't even know we should be looking for. What this all adds up to is a really fundamental change in how we do science. We are moving away from a big data world where the challenge was just getting enough data to a smart data world where the true bottleneck is our own imagination. FSL is a tool that helps us break past that limit. And that leaves us with one final fascinating question to think about. We've seen how FSL can filter, bridge, and sieve our data for us. But what's the next step? What happens when these systems become true AI co-scientists? When they not only analyze our results, but start helping us figure out what questions to even ask in the first place? That is the future that FSL is starting to unlock.